Hello and welcome to this new unit on energy and work. So far we have gone through kinematics, we've gone through forces, we've done some circular motion, we've done gravitation, we've even talked about momentum. Really, those can be broken down into three main topics: kinematics, forces, and impulse and momentum. We're now going to learn our fourth and final topic in our mechanics section of this course, and that has to do with energy and work. You can think of those three previous topics as tools to use when trying to solve some sort of question. Any question that you have seen so far in physics can be analyzed in one of basically three different ways. Either you're going to apply some kinematics equations to figure out whatever it is you're trying to figure out. You might have to draw a free body diagram and write net force equations and use forces. Or you have a situation where you invoke the rule of conservation of momentum. When we talk about energy and work, this is going to be another tool for you to use. And a tool that might be more useful in some cases than in others, and sometimes it's going to be more useful than any of the other tools that you have, just like everything else. So to start off, as review, we have a picture that shows a ramp and an object on the said ramp. We want to know, how could we determine the final speed of an object if it was released from the top of a frictionless ramp from rest? So we have a lot of good information here, okay? And let's say that we know a few other things. Let's say that we know the mass of the object is m, and we know that the distance it slides to the bottom is d. Well, how could we determine how fast it's moving once it gets down to here? It's a frictionless ramp. It's released from rest, so that means the initial velocity is 0 meters per second. It's frictionless, like I said. How do we determine how fast it's moving down here? Well, if you think about it, we know that we're probably going to have to use at least a couple of different of the tools that I mentioned before. Conservation of momentum does not seem super likely, just because impulse and conservation of momentum and momentum in general. It doesn't seem likely because there's only one object here and there's only one object at the end that's moving that we care about. Seems like something that would be more useful to do maybe some forces and kinematics. Now, when is kinematics useful? Kinematics is useful when you already know the acceleration. We don't know the acceleration of this object. Matter of fact, one of the ways that we've talked about how to find the acceleration is to use forces, to draw a free body diagram and write a net force equation. So as far as our steps go in solving this, I think the first step would be draw a free body diagram. Okay, think about it. This is what you would do first. So our free body diagram might look something like this. Here's our object of mass m. We're going to tilt our axis since we have a ramp and we want to align the ramp with the direction of the acceleration. If it's frictionless, we can assume that this box is going to be accelerating down the ramp. I have the force of gravity pointing straight down, and I have a normal force pointing in the positive y direction. That's not straight up. Instead, it's at an angle to be perpendicular to the ramp surface. Not just an angle because we feel like it. It's because it's literally perpendicular to the ramp surface. That's the definition of normal force. Based on this, we do have to split Fg into components because it's not aligned with our axis. That'll look something like that. I'm going to cross off where m is. I'm going to write it over here. Now, if you remember from ramps, the component that is perpendicular to the ramp surface, that would be this one right here. Here's the ramp surface. That's perpendicular to it. That is the one that is Fg cosine theta. The other one is Fg sine theta. And if you remember, this shows us that for ramps, because of how we set up our free body diagram and our axis and our angle, cosine and sine switch from what they normally are. Usually, you use cosine to find the x component and sine to find the y component. That's not the case here. Okay, so we've got our free body diagram. That's completely drawn. If you need more help with the free body diagram, I suggest going back and looking at some of the ramps videos. What do we do immediately after drawing a free body diagram? We write net force equations for the x and y direction. Well, that would look like this. We have F net x equals Fg sine theta equals max. Fg can be written instead as mg, so mg sine theta equal max. And then you notice I have an m in both terms, so I can cancel those out. If I divide both sides by m, they go away. I'm left with this. The acceleration in the x direction down the ramp is g sine theta. And actually, that's all I really need. I suppose I could do the y direction and do f net y equals fn minus fg cos theta equals may. The object is not accelerating in the y direction, so may is 0, and we're left with fn equals mg cos theta. But that's not really going to play a role in the rest of this. The whole point of doing a free body diagram and net force equations is now I have an expression for the acceleration. Okay. By the way, if we were actually doing this, we would know what this angle is right here, the angle that the ramp makes. So if we know the angle and we know the acceleration due to gravity, which we do, we know what g is, 9.81 meters per second squared. We know the acceleration, and once we know the acceleration, we can find whatever kinematics variable we want by using some kinematics equations or equation. Matter of fact, in this case, we only need one. So our last step is to use a kinematics equation to solve for the final velocity, the final speed. That's Vf. The equation that's going to work out easiest for us here is Vf squared equals Vi squared plus 2AD. I know the distance that slides is d. I know the initial speed is 0. I'm looking for the final speed, and I now know the acceleration. So now I have Vf squared equals 2 times g sine theta times d. And if I want Vf by itself, I just take the square root of both sides, and I see that the final velocity is equal to 2 times the acceleration due to gravity, 9.81 meters per second squared, times the sine of theta, whatever the angle is, multiplied by the distance that it slides. Now, I didn't give you those numbers, but if I did, now you could solve it. As a matter of fact, if I changed around those numbers, the distance, the angle, then you could still solve it because you have what's called a symbolic solution here. Okay, this works in any case. This is the final velocity for any case in which we have an object on a frictionless ramp. We want to know its final speed at the end of the ramp. That's great. Okay, it's kind of a lot of work. There's two different things that we have to do, or really three. A free body diagram, but that always gets paired with a net force equation right after, and then we have to use kinematics. That's a lot of work. Okay, it's not undoable. You should be able to do that, but that's a lot of work. Now, what if we look at a ramp that's slightly different? What if we look at a ramp like this? You'll notice that we now have, instead of just one smooth ramp, we now have two different sections to this ramp that have different angles. So that's interesting. The key thing there is while this is a constant slope, this ramp does not have a constant slope. Matter of fact, it has two different slopes. So think about what we'd have to do. Our free body diagrams would be different. It would be a differently angled free body diagram on this part and on this part. So we'd have to have two different free body diagrams. We'd have to have two different sets of net force equations. And then we have two different accelerations for here and for here. And then we have to have two different kinematics equations that somehow are linked together. You're doing twice as much work. So would have to do the previous work twice. And there's even one more point of confusion. What happens here? What happens where the slope changes? Does the box just kind of skim right across this? Does it get stuck in this little wedge? Does it flip over and slide on its short side? Does it somehow just kind of bridge the gap? What is the acceleration while it's going over it? Is it the initial acceleration and the final acceleration, or is there like a change? We have no idea. There's no way to tell, okay? Unless you were to do this and know a lot more about what's going to happen to that object, there's no way to tell. I don't think kinematics and forces would be very useful at giving you a very good answer here. It'd give you a very good answer here, okay, very accurate. Here, I don't think you would be all that accurate. If we look at our last example, this is taking that second example to the extreme. Instead of having two different slopes with one little kink right here, we now have a constantly changing slope. And if you remember that the slope, that the angle of the ramp, essentially what is determined by the slope, you know how that started, or that allowed us to find the acceleration? Well, if the angle of the ramp is always changing, okay, the slope is always changing, that means the acceleration would always be changing. We don't deal with constantly changing accelerations. That's not what we do in this class. All right, so if there's a constantly changing slope, that means that there must be a constantly changing acceleration, which would mean you need an infinite number of free body diagrams for each point on here, infinite number of F-naught equations, an infinite number of kinematics equations in order to figure out what the speed at the bottom here is. While, we have a lot of time to discuss these sorts of things. We actually really don't, but we have a good amount of time to discuss these sorts of things, but we don't have time to do an infinite number of free body diagrams. This is too much time. This would take too long. There's got to be another way. As a matter of fact, there is, by looking at these concepts called energy and work. So, as you can see, not all problems are easily going to be solved by forces. You can't just use forces and kinematics for everything. They're a good tool in situations where we have constant acceleration. If you can take one thing away from why we use different tools in different cases or different concepts, it has to do with conditions. Forces and kinematics are great when the acceleration is constant. Remember that, okay? When the acceleration is constant, forces and kinematics are great. In other situations where you might have a changing acceleration, we can instead use this concept called energy. I'm going to give you the definition, and the definition is going to frustrate you because it sounds like a bunch of gibberish. Here's the definition of energy you would see in, let's say, a textbook. Energy is a number associated with a system of one or more objects. A number associated with a system of one or more objects. What does that actually tell you? Absolutely nothing. That tells you literally nothing. It's very frustrating, but that's the actual definition of energy. Let's get a better kind of sense of what we're dealing with here. Here's how you can think of energy. Energy is the capacity or the ability of a system. Now, let's talk about the word system. System just means a collection of objects. We've been studying objects all year. System is just more than one. To have or potentially have motion. If a system has energy, it is either in motion or with a few changes, it could very well be in motion with nothing else happening, just if you remove a couple of barriers, okay? That's what energy is. It's still kind of frustrating. Really what energy is it's a way that people have found to solve problems, okay? It's someone discovered, I don't even know who, someone discovered a while ago that if we perform some certain calculations, we can make all the predictions we've been making about velocity and distance and time and speed and all that stuff and acceleration without going to forces and kinematics, okay? You can think of it kind of as, you can remember, conservation of momentum was kind of a shortcut for solving questions about collisions. Energy is kind of similar. It's sort of like a mathematical shortcut to analyzing certain types of problems that otherwise would be really tough to analyze. Okay, that's the best I can give you for energy. And even if you take like more advanced college classes, that's essentially what you're going to get. Okay, I've heard some people say, "Oh, energy. Think of it as the ability of something to cause pain or something like that," which is a little morbid. But that's not a bad way to think of it. Really, what it is, or what it comes down to, the ability of a system to either be in motion or, given a few changes, to potentially have some motion at a later time. Before we get to energy, we're going to first talk about the idea of work. And work is nice because work is defined based on some concepts you already know about. The definition of work is the transfer of this energy thing between two objects or systems, or between different types of energy. Here's the important part: by a force. We're going to underline that part. By a force. Okay? So, last unit we talked about how impulse was a change in momentum. This unit we're going to talk about how work is the change in energy or transfer of energy from either one object or system to another, or an exchange of energy between two different types. There are different types of energy, which we'll talk about in a future video. Okay, so work is the transfer of energy between either two objects or systems. So one object gains, one object loses, or system, or taking it from one type, or energy being transferred from previously being one type of energy and getting changed into another type of energy. There's a formula for work, and this is where I said previous concepts are going to come in handy. The formula for work is W for capital W for work equals F times D times the cosine of theta. Okay? So work equals force times displacement times cosine of theta. So let me write that down for you. Work is obviously W. F is force. D is displacement. Very important that you realize it's displacement and not distance. Okay, it has to be displacement. And theta is the angle between the force and the displacement. Okay, so force is a vector, displacement is a vector, theta is the angle between those two vectors. Even though we have two vectors here, work actually ends up being a scalar. The direction doesn't matter. And this is a little confusing because it matters whether work is positive or negative, but you'll never say that work was done east, or this is 20 units of work west, or north, or up. It's just work was done. It can be positive or negative, but it's simply work was done. The units of work, as you can see from this, units of force are newtons. The units of displacement are meters. Once you take the cosine of an angle, the angle is in degrees, but the cosine of the angle, that's unitless. So we have Newton meters, or if you remember what a Newton is a kilogram times a meter per second squared. So this could be written as a kilogram times a meter squared, because I'd have a meter on top for the newtons times this, over second squared. Or, instead of writing all of that out every single time, there's a better unit. It's called the joule. Capital J, don't get it confused with impulse. Joules. Okay, the units of work are joules. Now, real quick before we hit two examples before this video is out, how do we tell if work has been done by a force? How do we tell if energy has been transferred between objects or one type of energy increased and the other type decreased? Well, the force on an object obviously can't equal 0 and acts on object. So you'll notice that we said that the work is done, that work is a transfer of energy by a force. Forces transfer energy. Forces do work. Okay? We can talk about how much work people have done, but we really, or other objects, but we really need to be talking about how much work is done by a certain force. Forces do work. Okay? Forces are the vehicles that do work for a system. So if a force has done work, then obviously that force can't be equal to 0. If we have 0 times a whole bunch of stuff, that's going to be equal to 0. And the force actually has to act on the object. Okay? If you have a force that's, some size, but it's not acting on the object in question, well, guess what? It doesn't do any work then. That's one condition. So the force has got to be non-zero. It's got to act on the object. And in order for work to be done, the object moves in the direction of the force. So what that means is that the displacement has to at least be aligned with the force, at least a little tiny bit, at least one little component of it has to be aligned with the force. If they are in directions If it's not aligned, then no work is done. And as we go through the examples, you'll see more about what that means. Now, on your reference tables, real quick before we hit these examples, I do just want to point out on your reference tables, the equation for work is given as F times D. I really want you to include this. Work is force times displacement times cosine theta. F times D is fine if you're going with the simplest, most easy explanation of work, but there are questions where that doesn't quite, well, for lack of a better phrase, work out. You want to use this, okay? So even though your reference tables is just F times D, you're going to use this entire thing. Let's do an example. How much work is done by your applied force? Okay, so we're talking about work done by the applied force. If you lift up a 0.5 kilogram book, there's the mass, straight off the floor, and place it on a shelf that is 2 meters high. Well, I'm looking for the work done by the applied force. So here's what I'm going to do. I'm going to write W, and I'm going to put a little A next to it because I know I'm talking about the applied force. That's got to be equal to the force I'm talking about, the applied force, times the displacement, times cosine of theta. The only thing I really know here is the displacement. I know it's 2 meters. I know a mass, but I don't see how that helps me find either of these. If you get to this stage and you're like, I don't know how to calculate this, relax. Let's draw a free body diagram for this. Here's the book. If I'm lifting the book up, oh, I need an axis. If I'm lifting the book up, then I'm applying an applied force upwards, and there's also a force of gravity downwards. And I should note that this doesn't go on your actual diagram, but you can write it to the side. The displacement is upwards. So actually, that does help me out. If the displacement is upwards and the force is upwards, they are in the same direction. Two vectors that are in the same direction are separated by 0 degrees. So that's what I plug in here. Remember, theta is the angle between F and D. If there's 0 degrees angle between F, A, and D, then this becomes the cosine of 0, and in a minute we'll talk about what cosine of 0 is. What I need to do now is calculate what FA is. I can do that using a net force equation. F net Y equals FA minus FG equals MAY. Let's make this as simple as possible. It doesn't tell us that the book is accelerating upwards or not. Let's just assume that the acceleration is 0. Therefore, FA must equal FG, and instead of writing FG, I'm going to write MG. So I can calculate the applied force by doing this. The mass, 0.5 kilograms, multiplied by the acceleration due to gravity, 9.81 meters per second squared. FA equals 4.905 newtons. Now I can plug that in here. The work done by the applied force is 4.905 newtons multiplied by the displacement of 2 meters times the cosine of 0 degrees. Well, the cosine of 0 degrees is 1. So I'm not going to cross this off and write 0. I'm going to cross this off and write 1 because I know it doesn't really matter. Anything times 1 is just itself. So in order to find the work done by the applied force, 4.905 times 2, the work done is 9.81 joules. Now what does that mean? What that means is that the work done, 9.81 joules of energy has been transferred. Okay? In this case, and we'll get into how the energy is being transferred later, the energy went from you picking up the book into the book itself. There was a transfer of 9.81 joules of energy. Yeah, I can do the next one. Okay, how much work is done by gravity if you, mass of 70 kilograms, jump straight down off of a 1.5 meter ledge? This one, we're not even going to have to do a free body diagram. I know that the force of gravity points down, and I know I can calculate it very easily, and the displacement is also down. So the work done by gravity, WG, equals FG times the displacement times the cosine of theta. I know that the force of gravity is equal to mg times d times the cosine of theta. Now I just need to plug in. The mass is 70 kilograms. Acceleration due to gravity is 9.81 meters per second squared. The displacement is 1.5 meters. Let me move this up a little bit. And the angle, look, FG and D are in the same direction, the force and the displacement, the force that we're talking about and the displacement of the object. So that means there's an angle of 0 degrees between them. we know the cosine of 0 is 1. Therefore, the force of gravity on this object, or excuse me, the work done by the force of gravity, not 70 times 9.81 times 1.5, the amount of work done is a little bit over 1,030 joules. Again, what does that mean? I know there's not a lot of context for this for you guys right now, but what that means is that the work done of being 1,030 joules, that's how much energy was transferred, in this case, between two different types of energy. And again, we'll talk about how you know what the energy transfer means later on. Right now, I just need you to be able to calculate that energy transfer. 1,030 joules of energy was transferred between a source and where it ends up. In the next video, we'll do some more examples with work. We'll see a couple different situations. All right? Talk to you later.